In this recording, I'll have a quick overview of the relationship between electrical potential energy, electrical potential, electrical force, and electrical field. Now, in this case, we have a situation where we have a constant electrical field. It's represented by these red arrows here. So if I take a charge Q and place it in that electrical field, that charge is going to be subject to an electrical force given by Q times E. So if the charge Q is positive, the electrical force is going to have the direction shown, the blue arrow. If the charge were negative, the force is going to have the opposite direction. Now, the question here, what would be the work done by the electrical force if we move that charge from position A to position B? What would be the work done by this force? Remember, work is given by dot product between displacement and force. So in this case, it is, since the force is QE, just Q times the dot product between the displacement and the electrical field. If the electrical field is constant, that's basically it. So it's going to be, in this particular case, if I have an angle here, it's going to be QSE cosine of theta. That would be the work done by the electrical force. In general, if the electrical field changes, depends on the position, then we'll have to integrate instead of just doing a simple calculation. In this case, we have a constant electrical field, so my work is just Q times S times E. I'm not sure why I jumped to the next line, but anyway. Since the electrical force is a conservative force, it's not a lossy force, it's not like friction or air resistance, then the change in potential energy due to that force, in this case, since it's an electrical force, that would be the change in electrical potential energy in moving the charge from A to B is going to be UB minus UA. It's going to be the negative of the work done by the force. That's the definition of potential energy, general definition of potential energy. So in this case, it's going to be minus QS dot E. And again, if my E changes, if my E were not constant, we'll have to integrate instead. Now, what we define as electrical potential is electrical potential energy per unit charge. So it's U over Q. That's all what it is. So whenever we have an electrical field, we are going to have an electrical potential. That electrical potential, it is a meaningful quantity that has a value that tells us of how much a charge would have in electrical potential energy if we place it there. So now, electrical potential would be UB over Q minus UA over Q. So using the formula that we talked about, it's just this. The unit of electrical potential is volts. And what's volts? Remember, where did we get the electrical potential from? It is electrical potential energy over charge. Electrical potential energy is joules, charge coulombs. So the volt is joules per coulombs. Another unit that's often used in physics to talk of electrical potential is what we call the electron volt. We are not going to use it much in this course, but 1 electron volt is 1.6 10 to the minus 19 joules. Okay, I'm not going to go much more into it. So to find the potential at every point, what we do is assume it to be equal to 0 at some point, at point A, for example. And then we find the potential at the other point by using the expression that we talked about, by using the expression that we had here. So minus from A to B of E dot ds. And if E is constant, it's going to be just minus E dot s. Okay? Now let's look at an example. That's an important example. What if we have a large conducting plate with a positive charge, with a sigma here, surface charge, being positive? Remember, sigma is going to be Q, the amount of charge, over area. Now, from what we have learned before, I hope, the electrical field due to that charge on top of the plate or below the plate, so we have two arrows representing them, in either case is going to be given by this expression, sigma over 2 epsilon 0. That's the electrical field due to a large charged plate. So if we set the electrical potential to be 0 at A here, A on the plate. Now at point B here, I can find the electrical field using that expression. Again, since here E is constant, I can factor it out of the integration. And then it is just minus h times E, where h is that distance going from A to B. So then my electrical potential is just minus sigma h over 2 epsilon 0. Same thing if I went the opposite way. The electrical field is in this direction, displacement is in this direction, so we are going to find the same expression. So the potential at C is minus sigma h over 2 epsilon 0. At A, it is 0, since we set it up as 0. And then at B is given this. Remember, the value of B depends on the value that we have chosen for A. What really matters is the difference between A and B. That's why we can set the value of A to whatever we want. We can set the 0 whatever we want. Let's talk a little bit more about this. Just one more thing. Okay, so in this particular case that we talked about, this is the expression of the potential. So what does that mean? So if I have a positive sigma, my potential is 0, is negative. My potential is negative the whole time. It is 0 at A, and then it is negative the whole time. So as I move in the positive direction away from A, I get these values. If I move in the negative direction, I get these values for V. Now, if sigma were negative, we'll have the opposite. Moreover, the electrical potential depends only on h. That's the only changing thing. So if I have the same distance h, like these dashed lines, I'm going to have the same potential in them. So we call them equipotential lines. And in here, they are parallel lines. Okay.